Forward to the cloud. Right, so a radical expression, well, this is the old statement of the year, is an expression that contains a radical sign. Oh, yeah, it's like defining a word using the word in its own definition, right? But you might have seen a radical before. What we're going to do is focus on square root radicals, right? So this is a square root radical because the index is equal to 2, right? So if you have something that's in the form, so for example, if I had radical 8, well, I have 18 there, so I don't want to use that again. Radical 9, that's a square root radical. If I have something like, a little 3 inside that little cusp there, that would be a cube root radical. All right, so that little cusp there is where you put the index of the radical, indicating what type of root you're trying to take. So when we talk about a square root radical, we're talking about 2 numbers that multiply to the thing under the radical. Now we're only going to worry about what we call principal square roots. So it is possible that you could have negative numbers that multiply to the value under the radical. So when I say find the square root of 9, I'm saying give me 2 numbers that multiply to 9. So you might say 3 and 3, but you might also say -3 times -3. That'll do the job too. We're only going to focus on the positive cases because it's a geometric context, right? There is room in geometry for negative results of square roots, but that's not going to be the focus, at least of this lesson, right? The cube root would be 3 numbers that multiply to whatever that radicand, the thing under the radical, call that a radicand. The cube root would be a number that when multiplied by itself for a total of 3 factors multiply to that number. So in the case of the square root of 9, that 9 is what we call a perfect square, right? Because if I look to find, you just using ordinary calculator functions, the square root of 9, I get a whole number as a result, right? But if I try to find the cube root of 9, that's a different story altogether. Different story, right? Actually, I've been meaning to look this up. I don't think that there's a shortcut in Desmos for finding a cube root. Oh no, there it is. I never bothered looking before. It's there. Right. So if you go into functions and you go all the way to the bottom, you'll see one that has an n with a little, looks like square root symbol, but it's really a radical. So it allows you to put an index in. And you see here that I would be looking at the cube root of 9 as being 2.08 blah, blah, blah. Now, the reason I bring this up is because people tend to think when looking for 3 numbers that multiply to 9, they say, oh, I'll just take the 9 divided by 3 and just call it a day. Well, 3 times 3 times 3 isn't equal to 9. But 2.0800838, my vision is shot here, 2305 times itself 2 more times would give you a 9, right? So you could have under the radical any number. I can never make a small radical. Okay, I just proved myself wrong. You could have any number, I'll call it A. This would be read as the nth root of A. All right, so you could take any root you want. It's just it gets more and more complicated when you increase the value of the index. Again, the thing that's in the little cusp of the radical, in that little Well, it's not really a cusp. It's like that little V area, a little wedge, you know. So what we want to be able to do is focus. Well, we're going to focus on the square root radicals. So that's this situation. Because we're working in 2 dimensions, the most we're going to need to do, at least for now, is multiply 2 numbers, right? So if we had to go the other way and figure out what 2 numbers resulted in a particular value, let's say, for example, if I knew the area of a square was equal to 18, and I wanted to know the length of each side, I would have to find the square root of 18, right? So if you expand the dimensions, instead of working with 2 dimensions, you work with 3 dimensions, which we'll get to later in the course. You might have to take a cube root. Again, not part of this lesson, but it'll come down the line. If I had a 10-dimensional figure, which would be unfathomable, without fathom, you wouldn't be able to really visualize that, but you could find the length of a side if you find the 10th root of the volume of that figure, right? So, a lot of applications of this, but we got to start off somewhere. So we start off with the 2-dimensional stuff, all right? So a couple of bullet points. Square root expression is in simplest form if the radicand has no perfect square factors other than 1. And that's what we call the trivial case. The radicand has no fractions. There is no square roots in the denominator. Right? You could have technically more than 1 square root in a denominator of a fraction, right? Typically, we say that that's simplest form, but there are other types of simple forms of a radical. As long as you only have, if you have a fraction, as long as you only have a radical in one part of that fraction, your fraction is considered simplest, right? So I would amend this, well, really add on to say, as long as only one part of the fraction as a radical, right? So then it would be in simplest form, right? So that's the condition of the whole thing. So we could say no square roots in the denominator. We could also say no square roots in the numerator. Ideally, we wouldn't have any square roots in either, but we got to settle for some things, right? So when we look to simplify a radical, I included a list of perfect squares because nice to have something to point out. But you could also come up with this in Desmos, right? Or any other calculator. You just start squaring numbers, right? Because that 1 that you see there is actually 1 squared. The 4 is 2 squared. The 9 is 3 squared. 4 squared. 5 squared. 6 squared, all the way down the line. I skipped a few. Once we get further down the line, I'll show you what those are. 10 squared, 11 squared, 12 squared, 13 squared, 14 squared, 15 squared. But then I jumped to 25 squared, 30 squared, and 40 squared. Oh, and 50 squared. And these are the most popular perfect square values that you might expect to see. Right? So any of these perfect squares, when square rooted, if that's a term, would give you a whole number as a result. So for example, if I took the square root of 196, whole number as a result, 14. All right. So these are all perfect square values. So what we want to do, and when we're writing a radical in simplest form, is first check to see if the radicand, which is again the thing under the radical, is of itself a perfect square. But if it's not, we want to see if it's divisible by a perfect square. And if it is, I want to know the largest perfect square it can be divided by. All right. So what we want to do is find a factor, a perfect square factor closest to 1/2 of the radicand. All right. Closest to 1/2 of whatever the radicand is. Right. And again, radicand is just a number under the radical. All right. Radicand, 3 syllables, number under the radical. Right. You save yourself 5 syllables by saying radicand, as long as you know what it means. All right. So I look at, for example, in number 1, the 50. I'm looking for a perfect square factor. Now, I know the term factor tends to strike fear into the heart of everybody. Well, not everybody. Some people are really good at that. I got to say, I wasn't really good at factoring until, really being honest, I stopped having to think about factoring, whether it was algebraically or numerically, once I started teaching. So I mean, I got better and better as the years went on, but it wasn't until it didn't become like muscle memory until I was teaching. And that's because you do something every single day, it becomes second nature, right? So we don't have the luxury as students to do something every single day for a particular topic. I mean, you got other classes to worry about, things like that. But if you follow this strategy, you'll be able to simplify radicals fairly quickly and easily, right? So we're looking for a perfect square factor that's closest to half the radicand. And then what we do is we make a little tree diagram. I know it doesn't look much like a tree, but I don't know what else to call it. So I just call it a tree diagram. I mean, it's got some branches, so it's fine. But the closest perfect square factor to half the radicand, in this case, actually happens to be half the radicand. The number 25 is a perfect square. So the square root of 25, if I can get a dang radical to show up, you know what I'm going to do? Copy and paste. We're going to break this up into a product of the perfect square factor and whatever I'd have to multiply that perfect square factor by to get the original radical. Right? So 25, I'd be like, okay, well, what do I have to multiply 25 by to get 50? 25 times 2. Right? The reason why we do it this way is because, I can't break down the radical 50. If I try putting that in the calculator, it's not going to give me a whole number. But I can break down the radical 25. I can break down one of the factors of 50. Right? When we talk about factors, we're talking about two numbers that multiply. Well, it could be 10 numbers, but in this context, two numbers that multiply to another number. Right? So when I say, what are the factors of 12? You could say 3 and 4. 3 times 4 is 12. Right? So we're just looking for two numbers that'll multiply to the radicand, but one of them has to be a perfect square. Otherwise, we're not going to go anywhere with this. Right? And the reason why we can do that, or the reason why that's beneficial, is if I take the square root of 25, I get a clean 5 out of it. So the radical 2, I can't do anything with. Right? So I just bring that along for the ride. Now, the question that's always going to come, it always happens, it always occurs. How do I know I can't do anything with the radical 2? How do I know I can do something with the radical 50? That's where this stuff really becomes useful. Right? The first thing is the radicand, its simplest form, if the radicand has no perfect square factors other than 1. Right? Because I could, like this radical 2, I can break it down. Hey, one of the factors is a 1. That's a perfect square. It's even half the radical, the radicand. But find a perfect square factor closest to 1/2 of the radicand. All right, radical 1. Radical 1 times what? Well, it would be radical 2. What's the square root of 1? 1. What's the square root of 2? The square root of, dang it, we didn't accomplish anything here. All right, that's the trivial case. You can always break up a radical based off of factors involving a 1, a radical 1, and the number itself, but it's not going to get you anywhere, right? So in the case of number 2, for example, and if you're writing stuff down, don't write what I'm about to write down. I could look at this and say radical 1 times radical 108. And I'd say, okay, square root of 1 is 1. Radical 108, 1 times, same thing. One in a big old circle, got me nowhere, right? So what I want to do is start looking for factors at a value that's half of whatever the radicand is, right? And if that half value is 1, then it's already simple, right? So I'm looking at 108. Half of 108 is 54, right? So 54 is not on my list, but it's in this neighborhood. So I start looking for factors of 108 in this neighborhood, right? I can go to the left, I can go to the right of this marking. I can tell you it's never going to be to the right of that. So you can try, but it's not gonna happen, because once you go beyond half of a value, anytime you divide by that number, you're going to get a fraction, which is not a whole number. So if I looked at, for example, 100, and I said, all right, half of 100 is 50. And 100 is perfect square, so just bear with me. But if I said half of 100 is 50, and then I was like, okay, well, let me see if 60 will work, or 70 or 80. No matter what value north of 50 I divide into 100, I'm always going to get a decimal, right? So we start off at the half value and work our way down the line, right? So it's at this point it's trial and error, but I'll show you a couple of tricks. They're all Desmos tricks, very fancy stuff, but just bear with me for a minute. So 108, we try dividing it by 49. Decimal value, no good there. 36. There we go. We got our winner. So we work our way from the half value of the radicand downward, just trying values to see if any one of them are factors. Factors meaning they divide evenly into whatever the radicand is. So my two factors here would be radical 36 and radical 3. Now, these are all square root radicals, so I can just say radical because, there's no confusion. I'm not talking about a cube root radical or an nth root radical. So we could just say radical, or I like to shorten it up to rad. I know in science that means something else, but I'll say something like rad 6 or rad 3. I mean radical, which means square root in this context. Square root of 36 is equal to 6. We try it in here. The radical 3, I can't do anything with. There's no perfect square value that's divisible or that divides evenly into 3. All right, if I go to the half value of 3, that gets me to 1.5. The only value in my list that's less than 1.5 is 1, and that's the trivial value, the trivial case. It's of no help. All right. Now, the Desmos approach, I mean, I feel like I preface this any talking about Desmos by saying the same thing. It's not for everyone. Yeah. I'll save the Desmos once we create it, and I'll put it in Blackboard so you have it. But some people just aren't going to like it, and that's fine. Right. If you understand how to do it by hand, then you're good. You don't have to worry about the Desmos. If you don't understand how to do it by hand and you don't think you will, or you don't want to, then you kind of don't have a choice. You need some other approach. So let's just give it a shot and see how it goes, right? So when it comes to Desmos and simplifying radicals, you do need a list of perfect squares, right? So the way we handle that is by making a table. You hit that little plus icon and select table, right? I like to change the headings on this for no other reason than it's easier to type in variables if there's no subscript associated. So I'm going to go up here and change this to like, it could be whatever you want. I'm going to make it an N. All right. And then I'm going to just start typing numbers. Right. So literally typing numbers. So starting literally, no, numerically. 1, 2. After I type in the first two values, it starts populating values in for me. Fortunately, that's what I want to do. I want Desmos to come up with a list of perfect squares for me. I don't want to have to do it myself. Right. So like I don't want to manually figure out what 1 squared is, 2 squared. Apologies, folks. It took a while, but for some reason, I am only now noticing that I accidentally wrote 2 cubed here. Right. So 3, enter, 4, enter. It's auto-populating, so you can just hit enter a bunch of times. Do it as many times as you want. You know, I skipped values between 15 and 25, but it's so quick and easy to hit enter over and over again. You even hold it down. Well, on a keyboard, you can hold it down and it'll keep going. On a tablet, it's a little different story. You got to do like the reverse flash, like hand vibration move in order to get it to go really fast. But you can go, I mean, I'm already into the low hundreds here without really putting much effort. You know, I can kind of zone out, you know, if you're looking for something mindless. Reminds me of when I would go to my father's office when I was younger, you know, stuck sitting in his office for hours. I really got a good handle on the powers of 9. Like crazy what you're willing to do after you've attempted every puzzle in the newspaper. There were newspapers back then, no internet. He had a little adding machine there, and I was like, all right, 9 times 9 times 9 times 9 times 9. And I just kept doing that. That's how I know 9 to the 4th power is 6,561. I'm just going out to 500 here for fun. Really, mostly to demonstrate how quick you can get this done. I mean, you don't have to do it, but you know, the more exhaustive you make the list, the more useful it'll be for you. Right. But you'll also see that they truncate. All right. So it goes 1, 2, 3, 4, 5, 6, 7, skip a few, 497, 98, 99, 500. And there's 489 more rows. And you could select show all if you want to see them all. It'll give you everything. Or you could just tap anywhere else and it'll truncate it for you, which is really kind of nice. Right. Now I have those entries. What I want to do is I want to square every one of them. So in my, where it says Y1, I'm going to type in N squared. And it's going to take every one of those values of N and square them. All right. It also makes a graph if you're interested in what this might look like. It's fun. Part of a parabola. You remember those things? All right. So now I have a list of perfect squares that go out to 500 squared. Right. That's great and useful, but I want it to help me even more because I want it to give me the factors of radical 20, for example. I want the two numbers that are going to multiply to radical 20, one of which should be a perfect square. That's what I want Desmos to do. it's great that it's given me a list of perfect squares, but I want it to do more. It's technology. It should be able to handle more. All right. So what I can do this one of two ways. I can go into a third column and type 20 divided by n squared. I mean, the graph is like going crazy here, but we don't really care about the graph. We care about the table of values. All right. I'm trying to do this without going full screen. I might have to. All right. Well, the touchscreen aspect of this is not ideal. All right. But anyway, these are all the values that you would get if you took 20 and divided it by the values in the n squared column. Right. But I want something even better than that. I want something that's going to work for every problem. So I'm going to take, and you can use whatever letter you want. I'm going to take a capital R for Raticane. It's going to tell me I did something wrong. Well, that's fun. Right? It blanked it out. It gave me this little error message that tried defining R. Down here in a new field, I'm going to type in R equals 20. Equals 20. All right? The benefit of doing this, it'll produce the same list that we just had, except now I have a slider. Right? And that slider is really useful because now I can change the value of R and it'll change the whole value of the table. Right? Trying to, there was a, yeah, you just gotta want it. That's really all it comes down to. I want to try to expand this a little bit more. Yeah. I guess I didn't want it enough. Yeah. Come on. Okay. The split screen is kind of interfering with it, but I'll just do this kind of like tucked away in the small window over here. All right. So 20 would have factors that are in the second and third column. If you look at the first entry here, 1 times 20, 1, 20. 1 times 20 is 20. 4 times 5. 9 times 2.2 repeated, right? So using the same strategy, what we would do is we'd start off at the value that's half of 20, right? It's not in my list of perfect squares, which is the n2 and n squared column, but the closest value to that is 9. We go up the list here, starting with the 9. All right, so going up the list, well, 9 didn't work because the other factor is decimal, but 4 works because the other factor is a whole number. And the only other case that works is the trivial case, the case involving the perfect square of 1. So this is telling me that the appropriate factors would be the square root of 4 and the square root of 5. And the square root of 4 is 2, right? So you kind of work backwards in the table. And the radical 5 you can't do anything with. If you're good at recognizing prime numbers, those are the numbers that can only be divided by 1 in itself, then you're kind of in good shape because prime numbers are already in simplest form. They're not going to be a product involving perfect squares, right? But that would be 2 radical 5. Right? So then you get into other cases, much more substantial cases, but they're all based on the same thing. We have to simplify a radical, but in the case of number 4, we also
Yes.
Was there a question there? We have the radical 200, we have to break that down, but then we also have to simplify the fraction. Right? So that radical 200, what I would do is I would just kind of pull that off on the side. I don't even know why I keep trying to make radical symbols. I'm going to break that down. I'm going to start off in my list in the n squared column with a number that's half the value of the Raticane. Well, fortunately, that number is in the list, right? So, oh, actually, that 100 is in the list, which is great. But this list here, the R over N squared, that's no longer relevant because that's involving a radicand of 20. I need that to be 200. So what I would do is go down here and change my 20 to a 200. And so now, see that top entry here is a 200. I look at my 100. 100 times 2 is 200. 100 is a perfect square. So that would be my perfect square factor. And then the 2 is, well, it's not perfect and it can't be broken down any further. The square root of 100 is 10. So 10 radical 2. Now, questions 1 through 3, that was it. That's all we had to do. But now it's part of a fraction, right? So what I would do is I would replace this radical with this new simplified form. So I'm looking at 10 radical 2 over 2, right? Now, simplifying fractions is also a skill that's going to work its way into this. So you look at the 10 and the 2, you could ignore the radical. The radical's already been simplified. If I look at just the 10 and the 2, the 10 here and the 2 here, and say, what would I get if I simplified that? I'd look at this and say that they're both divisible by 2, right? So I could divide both by 2, and the result would be 5 over 1, right? So 5 radical 2 over 1, but we know that when you write something over 1, that's irrelevant. If I said 5 over 1, it's the same as saying 5. So 5 radical 2 over 1 is the same as saying 5 radical 2. All right. Now, calculators will simplify fractions for you, but very rarely will they simplify radicals for you, right? So whether it's Desmos or TI calculator, it's generally not going to simplify the radical, right? So you have to handle that, but the calculator can help you with all the other stuff. Right? So number 5 is the same general idea. I would look for a number that's half of the radicand, the 300, and look for that in my list. But I want to change, if I'm letting this capital R be the radicand value, I'd want to change the R value down here to 300. Now you see the length of the slider is actually expanding. So I can actually slide this to whatever I want now. Like if I had a problem that had a 150, I could just slide the slider to 150, right? Because the outer bound is larger. It's also going to allow for decimals, but you can change the parameters on the slider. It's very easy. All you'd have to do is just tap on one of the boundaries, like that -10. Just tap on it. It'll ask you what you want it to go in between, in terms of radicand. So maybe like 0 and 500. And we're really only interested in whole numbers, so you can make the step equal to 1. So from 0 to 500 going by ones, so that when I slide my slider, I'm not getting decimal values anymore, but I can slide it right to a 300. Sometimes with the touchscreen, it sticks a little. So you might resort to just typing it in anyway, but if you get it to land on it, it's fine. So in number 5, I'm doing the same thing in that I'm taking that radical 300, I'm pulling it out, I'm breaking it down into the product of 2 radical factors, one of which should be a perfect square, must be a perfect square. Well, if it's simplified, it's going to be a perfect square. I start my search at half the value of the radicand, which would be 150, so that puts me in this neighborhood. Then I start working my way down the line until I find a whole number. All right, whole number in the 3rd column. Right, whole bunch of decimal values, all these decimal values, but it isn't until we get to this case here where we have a whole number, as we start at the half value of the radicand and work our way towards 1. Right, so up the list, we get 103 under the radicals, respectively. Square root of 100 is 10. Square root of 3 is the square root of 3. So then we go back and replace the radical 300 with the 10 radical 3. So that gives us a new fraction equal in value 10 radical 3 over 3. Right? You can't divide a radical number by a non-radical number, right? We call those irrational numbers. Anything that has a radical in it is irrational. We wouldn't be able to divide the radical 3 by the 3. You can divide rational numbers, like the 10 and the 3, if possible. You can divide radical numbers if possible, but you can't mix and match. You can't take a radical and divide it by a non-radical, right? Same thing goes for multiplication, addition, and subtraction. All 4 operations, basic operations. You can't commingle the 2 types of numbers, right? So in this case, I would not be able to simplify any further because the 10 is not divisible by the 3, and those are the only things that I would be able to divide, and I can't, right? So then number 6, radical 54, again, same deal, same structure. I'm going to look for half of 54, right? I'm going to put in my radicand as my R value, so I'm going to run that down to 54. And this is really just so you know, I mean, you don't have to use this calculator here, but it's so that you don't have to test every value. Right, so I'm having trouble getting it to land on the 54, so I just tap on it, replace the 3 with a 4, and now I'm good to go. Right? So I'm looking at, again, same deal, same structure. I'm breaking down that radical 54. It's going to be a product of 2 radicals. That was a little obnoxious on the radical there. Obnoxious being the word of the day. Obnoxious. My obnoxious radical symbols. That's an obnoxious one. All right. The second one's a little more sassy than the first one, but we get there. So I look for half of 54, which would be 27, right? Not a perfect square, right? 27 is not a perfect square, but it gives me a place to start my search. I start decreasing from 27 to the neighborhood of 27 until I find a whole number in the 3rd column. That would be the case of 9 and 6. So 3 rad 6. The rad 54 gets replaced with the 3 rad 6. Now we want to be looking to simplify. No, not going to let me change the color in this mode. We're looking to simplify the rational numbers, the ones that don't have radicals. Right. So I'm going to reduce the 3 with the 6. All right. So they're both divisible by 3. So I can divide each by 3. Divide the top by 3, you get a 1. Divide the bottom by 3, you get a 2. And so you'd be looking at 1 times radical 6, which is just radical 6, over 2. All right. And one of the conditions of having a simplified radical is not having, or only having a radical in one part of the fraction. Right. So in these cases, we're not getting a radical in the bottom of the fraction, but we are getting a radical in the top. As long as that radical in the top is in the simplest form, you're good to go. So then looking at, well, you know what, I'll do number 9 because I can keep number 6 on the screen at the same time. You see that there's a coefficient in front of the rad 52. So we're only going to focus on pulling out the rad 52. I'm looking for two numbers, one of which is the perfect square. That's going to divide evenly into the radical 52 or the 52 itself. So I'm going to change my R value to a 2 here. Half of 52 is 26, so I start my search around 26, and I keep decreasing down the list here, down numerically, but up physically, until I have a whole number in my third column. That happens here with the 4. So 4 under a radical, square root of 4 is 2. Square root of 13, 13 prime, I can't do anything with that, right? So now in the numerator, I'm only replacing the rad 52 with the 2 rad 3. So I still have the 7. I still have the 2 on the bottom. It was 7 times 52, or 7 times rad 52 on the top. So now it's 7 times 2 rad 13 on the top. So we look to simplify that. There's 2 ways to handle simplifying that. One would be to multiply the 7 and the 2 and divide by 2. Another would be to divide any whole numbers that you can divide. Right? Anything that's, cases where they're divisible. So here I see I have a common 2. 2 divided by 2 is equal to 1. Those would cancel away, in each case to a 1. 7 times 1 on top is just 7. Rad 13 comes along for the ride, but I can't actually multiply the 7 and rad 13. The best I could do is write them adjacent to one another. On the bottom, I have a 1. So anytime you represent a fraction over 1, it's just the numerator. And so that would be my final answer. Right? And you can always verify. I mean, it's like I said, the calculator is not going to simplify for you, but it'll help you verify that what you did is correct. So if I type in 7 rad 52, and then on the bottom I pop in a 2, I get this disgusting decimal. If I type in a 7 rad 13, I should get the same disgusting decimal. And I do. So I know that at a minimum, what I just came up with is equivalent to what I started. Right? That's a good thing. We want that. No guarantee that what we just came up with is in simplest form based off of this technique, but at least we know we're on the right track. We know it's equivalent. All right. I'm going to streamline this a little bit. Actually, let me just kind of bring this back. So with 7 and 8, no denominators, but coefficients in the numerator. Right? So it's the same deal, just maybe a little bit easier. So I have the rad 72. I pull that out, I have a look at it. Rad 72, if I start off with factors, or a factor that I know is half of 72, like 36. 36 times 2 is 72. 36 is the perfect square. If the half value of the radicand is perfect, then that's the best case scenario aside from the number being a perfect square itself. Right? Square root of 36 is 6. So 6 rad 2. So I'm replacing the rad 72 with a 6 rad 2. I'm looking at 2 times, instead of the rad 72, 2 times 6 rad 2. All right, and the best I can do here is to multiply the 2 coefficients, the 2 and the 6, because those are the 2 rational numbers, the non-radical numbers. 2 times 6 is 12, so 12 rad 2. All right, and one more in this review of radicals. And we'll get to rationalizing in a couple minutes. We'll take a little break first, but let's take a look at number 8 before we do that. Same deal. We pull out the rad 54. Now we've already done rad 54. So one of the benefits of numerical mathematics, of computation, is that you don't have to reinvent the wheel. if you know, like for example, multiplication tables, you spend a lot of time when you were younger learning the multiplication tables. Yeah. So at this point, hopefully you could say 3 times 5 is equal to 15 without saying, okay, 3 times 5, 3 5 times, 3, 6, 9, 12, oh, 15. You don't have to reinvent it. So if you just figured out that rad 54 simplifies to 3 rad 6, you use that without doing the work, we would say 3 times the replacement for rad 54 is 3 rad 6. 3 times 3 is 9. Again, the two rational numbers get multiplied. So 9 rad 6. And the reason I bring this up, the whole like recognizing things that you've already done, is when it comes to triangle similarity, you're going to see the same kinds of radicals showing up over and over again. And so you can simplify, you can do the math, but in many cases, you're going to start to recognize that, oh, wait a minute, I've seen this before. And not just once or twice, but like 10, 15 times, right? So, before we take the break, let's just do 10 and 11 because they're pretty quick. So if you have a radical in one part of a fraction, you could move it to the other part of the fraction through a process called rationalizing, right? So what we do is we multiply the top and bottom by the radical you want to get rid of. Right, so multiply top and bottom by the radical you want to get rid of. All right. So in number 10, when I say rationalize the numerator, rationalizing means to make rational, right? And a rational number is one that does not have a radical in it in its simplest form, right? So basically, this is telling me that I need to get rid of that radical 2, right? So the way I handle that is to multiply the top and bottom of the fraction by a radical 2. That's equivalent to multiplying the fraction by 1, right? Because anytime you multiply by a number over itself, the number divided by itself is equal to 1, right? So we multiply across, when we multiply fractions, we multiply top times top, can't speak, over bottom times bottom. So on the top, you get rad 2 times rad 2, which is rad 4. Those you can multiply because they're the same kind of number. On the bottom, 2 times rad 2, they're different kinds of numbers, so I can't multiply them actually. So I would just say 2 rad 2. Right? So then you look at it and say, all right, is there more that I can do? And if there is, you have to. Right? It's not a question of want to, it's have to. So on the top, we have a rad 4. I mean, I keep calling it rad this, radical that, but ultimately what we're looking at is a square root. So whenever you see a radical, you're asking yourself, what is the square root of the number contained within the radical? So what is the square root of 4? Square root of 4 is equal to 2. All right. So then we can simplify because I have two numbers that can be divided here. Yeah, this color's fine. The 2 and the 2, they're both divisible by 2. So I divide each by 2. You get a 1 and a 1. So 1 over, well, 1 times anything is that, anything. So 1 over radical 2. All right, so this is the fraction that's rationalized in the numerator. Right, so I took the radical and I moved it to the denominator, but they are equivalent. If I type in a fraction with a radical 2 on top and a 2 on the bottom, I get that decimal. If I put the 1 on the top and the rad 2 on the bottom, I get the exact same decimal. So these two fractions are equivalent. rationalizing the denominator is the same skill, except I want to get the radical out of the bottom of the fraction. If I multiply top and bottom still by rad 2, top times top, bottom times bottom, 2 times rad 2 is 2 rad 2. On the bottom, we get rad 2 times rad 2, which is rad 4, which in turn is equal to 2. Now you start to notice little trends here. And, you know, like, hopefully this isn't the first time you're seeing radicals, but I'm kind of teaching it like it is, just because I never like to take the chance. When you rationalize, when you multiply a radical by itself, the result is always whatever was contained within the radical. So let's say, for example, I multiply radical 17 by radical 17. The result would be radical 389, but it would also be radical 17. I'm sorry, it'll also be just a 17. Right? Whatever was under the radical in each case is going to be the result. And that's because what I just wrote here is the same as radical 17 squared. Because anytime you multiply a number by itself, you're squaring it. A radical, a square root radical, and a power of 2 will cancel each other out. They cancel each other out to whatever is contained within the radical. Right? So you can jump from this computation here right to the 2 without doing that intermediate step. Right? But nothing wrong with doing the intermediate step if you're not sure. You'll still get to the same place. And I see here again, I got two numbers that are both divisible by 2. So 1, 1. So 1 times radical 2 is radical 2. On the bottom is just a 1, so I just leave it as the numerator. All right. If you want, you can use Desmos to simplify fractions for you. So for example, if I had, let's say 17 radical 3 over 51. I'll keep it simple. Actually, let me keep it simple by doing it this way. Make this a 30, and I'll make this a radical 10. All right. I can simplify this by using Desmos for the rational numbers and also the irrational numbers. All right. So I would create a fraction of just the rational numbers, just the ones that don't contain the radicals, 17 and 51. It'll give me a decimal, but that little icon next to it in the blue there says that there's a fractional equivalent available. So I just tap on that and it'll convert it over into the simplest fraction form. So it's saying that I can replace the 17 over 51 with a 1/3, right? But then I could do the same thing with the radical 30 and the radical 10, except I want to do it without the radicals because I know my answer is going to have a radical in it. It's just a question of where. So what I can do is I can take a fraction, pop in the 30 and the 10, knowing that I would have to put a radical over the whole thing. So this is giving me a 3. 3 is the same as 3 over 1. So this is the same as saying radical 3 over radical 1. So 1 times radical 3 is radical 3. 3 times, well, radical 1 is 1. So 3 times 1 is 3. Right? So you can do this with Desmos also, right? It's just, you got to do it in a very particular way where you're simplifying just the rational parts and then you're simplifying just the irrational parts, but you have to remember not to include the radicals. You know, so I can understand why people are looking at it and say, well, this is getting a little crazy, a little fast, you know? And especially if you were pretty good at simplifying radicals beforehand, you may not like the Desmos stuff at all, you know, but it's worth giving it a look because, you know, it can help. All right, so I'm going to pause. Let's take 5 minutes, and then we'll keep going. But we do have some more radical stuff to get through before we get on to applying this. All right, so I'll leave this up on the big screen. and let me pause the recording. So for number 12, rationalize the numerator for each, well, number 12 through 14, and then 15 through 17 is rationalize the denominator for each. All right, so some cases are easier than others. Sorry, question? So the radical 2 could be thought of as a radical 2 over 1. So if the first thought is, how do we rationalize a numerator if it's not a fraction? Hopefully that helps, because we think, okay, well, we don't always have to think about a number as just being a number. It could be part of a fraction, right? If I want to rationalize the numerator, I'm going to multiply top and bottom by rad 2. So rad 2 times rad 2, top times top, bottom times bottom, is going to be rad 4 over rad 2, right? The rad 4 on top, same thing as saying the square root of 4. The square root of 4 is equal to perfect square, so that's going to be equal to 2. So 2 over radical 2. So we have a number that's equivalent to what we started with, just with a rational numerator. All right. Now, it does say simplify and rationalize. Now, radical 2 can't be broken down, but radical 12 can. All right, so I would want to look at this. There's other ways of handling this, but generally, the approach I like to use is to pull out the radical, break it down, right? So you break it down into the product of factors. Right? The nearest perfect square factor to the half value of 12 is 4. So 4 times 3, square root of 4 is 2, 2 rad 3. So the 2 rad 3 replaces the 12. So we're looking at 2 rad 3 over 2, right? The 2's would divide out evenly. 2 divided by 2 is equal to 1 in both cases. So this reduces down to radical 3 over 1. Normally, I wouldn't write the over 1, but I need to rationalize the numerator for this problem. Right? So again, when you want to rationalize, you multiply top and bottom of the fraction by the radical that you want to get rid of. The one I want to get rid of is the radical 3. So on the top, rad 3 times rad 3 is rad 9. On the bottom, 1 times rad 3 is just rad 3. Square root of 9 is 3. So 3 over rad 3. Now I have an equivalent fraction that's equal in value to what we started with. Okay. Fair amount of work for something like this, only because of the part where you have to simplify. Right? You don't, like in the case of number 1, we didn't have to simplify the given radical, but it's possible. You don't want to find yourself in a situation where you're not able to easily simplify a radical, right? Because that could kind of bog you down. So that's why I was showing the whole Desmos thing. But maybe you didn't need that. And maybe you're good at simplifying radicals already, but definitely, like I keep saying, give it a shot. Maybe it'll be helpful. Right? So number 14, same deal. We want to simplify the radical, but we also want to clean it up so that there's only a radical value in the denominator, not in the numerator. Right? So I'm going to pull out that radical 32. I mean, it's the same thing over and over again, just some problems have more other things to do. Right? So rad 32, I'd want to be thinking about a perfect square factor. And again, go to your list if you're not sure. It's just, I didn't want to have to kind of expand the screen again, but the half value of 32 is what we would be looking at. Let me just get rid of some of these other computations. The radicand is 32. So I slide my slider to 32 or just type it in. So then I go into my table here and I'm looking for, kind of hops all over the place in this, condensed view, but half of 32 is 16 and that happens to be a perfect square. So then I would look for the counterpart, which is the 2. So that's how I know that this is a radical 2. All right. So the square root of 16 is 4 rad 2. So I would be replacing the rad 32 with a 4 rad 2. So I have 6 times the 4 rad 2 over 12. Now, I can use Desmos to reduce the non-radical parts. Right, the 6, the multiplication of 6 and 4, and also the 12. Assuming I don't want to just do it in my head because it's really not that bad. Right? 6 times 4 is 24. 12 divides evenly into the 24. But you could even, the simplifying fractions, you could even use it with products. So if I have the 6 times the 4 up top and the 12 on the bottom, it'll simplify for me. Right, so this is really 2 rad 2, right? So it's really the 2 merging from this computation and the rad 2 coming along for the ride because there's nothing that goes along with the rad 2. But again, I want to rationalize the numerator. And you say, well, this isn't a fraction, so let's make it a fraction. Again, you can take any number, put it over a 1 and make it a fraction. I want to rationalize the numerator, so I multiply top and bottom by the radical I want to get rid of. So when I multiply top times top, now this is kind of a weird case because you look at it and say, well, what do I do with this 2? Well, it comes along for the ride because in front of this radical 2, a little bit more of the theory of the numerical relationship. But in front of that radical 2, there's an understood coefficient of 1. So I'm actually taking this 2 and multiplying it by this 1. That allows me to, quote unquote, bring the 2 along for the ride. Then the rad 2 times the rad 2 gives me a rad 4, which is a 2. So I'm really looking at 2 times 2. So my whole numerator is going to boil down to a 4 in a second. But on the bottom, 1 times rad 2, again, I'm thinking of this as an understood 1 in front of the rad 2. Kind of like if you had a variable x. We don't really do much with variables in this course. But if you had a variable x, there would be an understood value of 1 in front of it as a coefficient. All right, it's the same idea here. A radical has an understood coefficient of 1 if there isn't an obvious coefficient. Right, so it's this 1 on the bottom here getting multiplied by this understood 1 coefficient of a radical 2, giving you 1 radical 2. Right, 1 radical 2 is just the same as radical 2. And so we get 4 over rad 2 as our final answer. For rationalizing denominators, it's the same stuff. Same story, different chapter. Because really all you're doing is the same stuff we did for the previous thing, except I want to move the radical from the bottom to the top. See how all the answers, 12, 13, and 14, all the answers had only radicals on the bottom. Started off with radicals on the top. Now we're getting radicals on the bottom, right? Now for 15 through 17, we have those radicals on the bottom. We want to move them out of the bottom into the top. So for the first problem, radical 7 can't be broken down because it's a prime number. Right? If you look at your list, your table of perfect squares, starting at 1, there's no number that's going to divide evenly into 7 other than the 1, right? So we don't have to worry about simplifying, but we do have to rationalize. We multiply top and bottom by the radical we want to get rid of. So that step that I've been taking for granted a little bit, 5 times radical 7 being 5 radical 7, again, that has to do with the fact that there's an understood coefficient of 1 in front of the radical 7, but you don't have to write that. I just did it in this case just to kind of make sure that I drove that point home. But when you multiply a rational number by an irrational number, the shorter way to do it is just write the two numbers adjacent to one another. So 5 radical 7, right? And on the bottom, 7 times 7 is 49, so rad 49. But again, you can skip that step and just make it 5 rad 7 over 7. Right? Because the square root of 49 is 7. It's perfect. For number 16, and really any question like 16, where you have a radical that can be broken down, even in the case of numbers 13 and 14, you can rationalize first, then break it down later on. It just usually ends up being more complicated to do it that way. So in theory, I could multiply top and bottom. You can multiply top and bottom of a fraction by whatever non-zero value that you want. Right? As long as you don't multiply top and bottom of a fraction by 0, you're good. Right? So if I wanted to, I could multiply top and bottom by rad 90. But then I'd still have a rad 90 in there that I would have to break down. I just find that it's a little easier to break down the radical before you get started on anything else. Right? So the rad 90, looking at its factors, we're looking for two numbers that'll multiply to 90, one of which is a perfect square. So, you might look at it and say, well, it's clearly 9 and 10, but maybe you don't. If that's the case, then you go to the table, right? Type in the 90. You start at the half value of 90, which is 45, so that puts you in this neighborhood. And then you're just looking for any non-decimal value as you work your way down the list here. And I say down again, down numerically, right? But 49 corresponds with a decimal, 36 corresponds with a decimal, 25 with a decimal, and so on. It isn't until you come to 9 where you find a value that corresponds with the whole number. So 9 times 10, square root of 9 is 3 rad 10. Right? So that tells me that I can replace the rad 90 with a 3 rad 10. Right? So 3 over 3 rad 10 simplifies nicely. I mean, as nicely as you can expect, because you can divide top and bottom by 3 and get 1, 1, leaving you with 1 over the square root of 10. But I want to rationalize the denominator, right? So rationalizing the denominator means that I want to have a rational number. I want to make the denominator rational, just like I did over here. Let me see the highlighter. So to do that, I multiply top and bottom by the radical I want to get rid of, in this case, rad 10. So 1 times rad 10 is rad 10. Rad 10 times rad 10 is just 10. Right? Because it's rad 100, square root of 100 is 10. The last one on this page is obviously different from everything else. It looks kind of weird, but it's really not that bad, right? Because the 7 and the 8, the 8 can be broken down a little bit, but it's not going to be too difficult to figure out what those factors are. But what people don't always recognize is that when you have the square root of a fraction, that's the same as the fraction of the square roots. So in this case, it's not a situation where I have a radical in one part of a fraction that I need to move to another part. It's the case where I have a radical in both parts of the fraction, and I just need it out of the bottom, right? So once I make that first move, I take a look at that rad 8. The half value of rad 8 is rad 4. Well, the half value of the radicand is 4. Rad 4 times rad 2, square root of 4 is 2, so 2 rad 2. So I can now replace the radical 8 with a 2 rad 2. So this is the same as saying rad 7 over 2 rad 2. So then I would be thinking, how can I get rid of the radical in the bottom of the fraction? I don't care about the radical in the top. I don't want a radical in the bottom, according to these instructions. All right. Now, you may have heard in the past that you can't have a radical in the bottom of a fraction. That's not true. You could have a radical wherever you want in a fraction. It's just a fraction is considered most simple if there is a radical in only one part of the fraction. And in most cases, people kind of adhere to the idea that you don't want to have a radical in the bottom, because if you need to add fractions together, it's nicer to have a common denominator that doesn't involve a radical, right? But that's not really that important, right? So we say we'll put the radical wherever we want, as long as it's in one part of the fraction only. So I'm looking to rationalize the bottom here by the directions. So top times top, bottom times bottom, right? So we're looking at rad 14 up top. Then the 2's coming along for the ride. So there's no counterpart to the 2 other than a 1. 2 times 1 is 2. You know, that understood coefficient of 1. Then I have rad 2 times rad 2, which is going to give me a rad 4. Let me lose this color here. And then we could simplify a little bit more. Rad 14 over 2 times, well, the square root of 4 is 2. So rad 14 over 4. Right. And that would be the simplest form fraction with a rational denominator. Right? You can see just by looking at the amount of work that I wrote, some cases involve more steps than others. 14 and 17 had the most, 12 and 15 had the least. It just kind of is what it is. The more stuff that's included in your fraction, the more you're gonna have to do with it. But I think that's kind of obvious, right? Because if I take a fraction and multiply it by a bunch of things, it's going to make it more complicated, right? So, and that's not even getting into cases involving addition and subtraction, which we don't really have to worry about for the time being. But yeah, that makes things even more complicated. Now, honestly, so looking at Pythagorean theorem on the next page, I'm about to be as surprised as you are, because I'm looking at that hyperlink that I included in these notes, and I can't for the life of me remember what the heck that is. So guess what? We're gonna explore that together. But for now, let's take a look at basic Pythagorean theorem. We get into a little bit involving the proof of it. So what you're dealing with is a squared. Well, the formula is a squared plus b squared is equal to c squared. But what you're really looking at are squared values giving you areas, right? When you square a number, the result is physically represented as a square, right? With dimensions based off of the squared value, right? So it's kind of a weird thing to think about, but when you look at this diagram, for example, and this got cut off here, so I'll take that as a typo. The area is equal to b squared, right? Now, the length of one side of a square is the square root of the area, all right? So if I find the length of one side, so length one side, or I'll say a side, is equal to the square root of the area, then the length of the side here is going to be the square root of b squared. I'm just going to kind of reduce this down a little bit. So the length of a side is the square root of b squared. Okay. So then we just have to think about what would that be? Well, it would be b. Right. And that's because, for example, I'll just kind of jot this off on the side here. We were talking about this before. If I tell you to figure out what radical 7 times radical 7 is, that's going to be equal to radical 49, which in turn is 7. Radical 7 times radical 7 can be written as radical 7 squared. All right. And whether you're doing it on Desmos or you're doing it in your head, radical 7 squared is going to be equal to 7. Because what's happening is the power of 2 and the radical are canceling each other out. All right, because they're opposite operations. All right. One is upscaling and the other is downscaling. All right. So I'm saying by saying 7 to the second power, I'm saying take 7 and raise it to the second power. When I say take the square root, I'm saying take that result and unraise it to the second power, which is just really going to bring you right back to where you started. Right. So all that's a fancy way of saying that the dimensions here of this square would be b by b. By the same reasoning, the dimensions of this square would be c by c. And the dimensions of this square would be a by a. When they say that a squared plus b squared is equal to c squared, what they're actually telling us is that if I take this square, actually, let me turn this, I don't want the shape tool on. If I take this square, see if I get it fit right, not too bad, and this square, put them together, I'm going to get, as a result, this square, physically. It looks kind of trapezoidal a little bit, but we'll kind of fix it in a second. But what this is saying, by the Pythagorean theorem, by the power of Grayskull, we're saying that this figure plus this, oh, that's too light. Would equal this. Right? So if I were to break these up and just kind of move them around, I should be able to manufacture this figure out of these two figures. All right. So, how that would happen is, a little bit more of a challenge, but it's doable with a little bit of patience and, really doable with a little bit of technology. All right. But that's the physical manifestation of this concept. All right. I'm just trying to remember what on earth that, I'm sure it was fascinating. Let me see. Let's find the weirdest stuff about me. Again, it's I'm not a fan of Justin Timberlake. It was my wife using the computer. No offense to Justin Timberlake fans. They go down this road every time. And then there's always like, why is he talking about Justin Timberlake? It's like, well, who said I was? Yeah, I can't. For whatever reason in this app, I can't just copy and paste a link. So that's why I'm doing this old school here. That's not an R. And B. I think I got it. We'll find out in a second. Oh, well, what do you know? I forgot that I found this online, and now here we are. Oh, this is exciting. This is a good moment, right? So this is actually what's happening. So we take the pieces of those two squared areas, you tuck one inside the other, and then you just start piecing it together. And that's how you would get a squared plus c squared is equal to c squared. It's not I mean, they call it a proof animation, but it's not really a proof, or at least a rigorous proof, but it's a good demonstration. I could change the size of the triangles, it gets, pretty big, but I change the size of the triangle to make it big and then resize it. And it basically goes back to where you started. But again, the animation just swings one square inside the other and then just starts piecing in the boundaries with everything else. So credit to Robin Farlow and Nick Cochise. No, I don't know these folks, but they did a great job, because that's a good animation. And apparently I found it at some point and put it in here and didn't think anything of it. But that's the justification of the Pythagorean theorem. Right now, when it comes to applying the Pythagorean theorem, it's actually much simpler. It really is. I mean, in terms of skill, nothing more than the ability to simplify some radicals, and in some cases, you don't even really have to do that too much, right? Because if you get some perfect squares out of it, you're in pretty good shape. So in the first one, we're solving for x, right? So it's pretty basic in terms of the instructions, but you have three parts of the radical that we're concerned with. One part is what we call the hypotenuse, that's the longest side. And the other two sides are known as legs. All right, we talked about this before when we were talking about proving triangles congruent. We have the hypotenuse leg theorem. All right, so here we're just working with it numerically, but either of the two legs would take on the role of A or B. Doesn't matter, they're interchangeable. So I can call this one A and this one B, or I can go the other way around and call this one B and I can call this one A. All right, those are interchangeable, and that's because addition is commutative. Right, you can add these two things in either order. So if you wanted to be a little bit more fancy or complicated, you could say b squared plus a squared is equal to c squared, and you're right. Right, that's another variation of the Pythagorean theorem. Right, so if I'm saying a squared plus b squared is equal to c squared, then I'm saying 6 squared plus 8 squared is equal to x squared. All right, 6 squared is 36. 8 squared is 64. X squared we're not going to do anything with just yet. 36 plus 64 is 100. So 100 is equal to x squared. If I want to find the value of x, we go back to that principle of opposite operations. If I want to get rid of a power of 2, one way I can do that is to take the square root, right? And we call this the principal square root because I'm only expecting a positive value, right? Because again, technically the square root of 100 could be -10, because -10 times -10 is 100, right? But we only want the positive because in this context, it only makes sense for the the length of the side to be positive. So the square root of 100, that's a perfect square value. You'll find that right in the list. Well, you'd have to expand it a little bit more. But 100 is right in the list of perfect squares. Its square root is 10. Now here, the power of 2 and the radical cancel each other out, and you're just left with the x. Right? Because if those two things wipe each other out, they cancel each other out, matter antimatter collision, they're gone. You're just left with the x. And so that would be the solution. That's the best case scenario. You get a nice perfect square. He gave you a diagram. They labeled the diagram nicely for you. But, as you've seen with some of the proofs that we've done, not always a case where they present the information to you in a nice, easy way. Right? So you're looking at number 2, a rectangle. Right? So a rectangle, not a square, but not particularly a square, but yeah, okay, so we know what a rectangle looks like. Opposite sides are congruent. Right? But it's not the case that all 4 sides are congruent. Right? They say that the length of the diagonal, well, they just have a diagonal of 20 feet, and the shorter side is 12 feet. Find the length of the longer side. All right, so that should be okay. And as long as you can, you visualize what a diagonal looks like. Now, later on in the course, in the next unit specifically, we'll talk about different characteristics of quadrilaterals, 4-sided figures. The diagonals are not always the same in length, but for a rectangle, they are. For a square, they are. Right? So if I draw my diagonal this way, or if I draw it this way, it's immaterial. They're both going to be the same length. Right? But if I had something like a parallelogram, let's see if that's going to lock to a parallelogram. Yeah. The length of this side is going to be shorter than the length of this side. Right? Those two diagonals will be unequal in length. Right? Not the case here, though. We can delay the inevitable there. But we know that this is good. Oh, that jumped on me. 20 feet. The length of the shorter side is 12 feet. The shorter side is the one that looks short, right? You drew the rectangle and with a particular orientation. Whatever you drew to be the shorter side is the shorter side, right? We need to find the length of the longer side. So we're going to look for this side here. We could just throw an X on there. Now, all of the angles of a rectangle are right angles, right? They're all 90-degree angles. So by drawing the diagonal, we've created a right triangle. So the Pythagorean theorem applies. Pythagorean, no. Gori theorem applies because there is a triangle with a right angle. I'll write the word out. All right, Pythagorean theorem applies because there's a triangle with a right angle. Now, you're going to see as we go forward that we're going to be dealing with triangles that don't necessarily have right angles. So what do you do there? There's other techniques. Something also to keep in mind, there's no way that you could have more than one right angle in a triangle, because that would put you over 180 degrees. Because if two of the angles in the triangle are each 90, then there's no way that you could have the third angle be anything greater than 0 and also satisfy the idea that there's 180 degrees in a triangle. Right? So I know my hypotenuse, which is the longest side, is going to be the 20-foot mark, or the 20-foot length. Right? So it begs the question of, well, how did I know that? The hypotenuse is always going to be opposite 90-degree angle in a right triangle. Right? So that usually kind of clears things up there. So that's going to be my C value. If I'm looking at A squared plus B squared is equal to C squared, I can write this as 12 squared plus X squared is equal to 20 squared. So that's 144 plus X squared is equal to 400. All right, so we're going to do a little bit of algebra here. It's not crazy algebra, basic algebra. There's ways around this algebra if you don't want to do it. I could show you that, but you know, in terms of the algebra that we're doing, it's not the most difficult. All right, so it's not factoring and completing the square and stuff like that if you're familiar with those ideas. All right, so I'm going to subtract off the 144. So I'm looking at X squared. Well, 400 minus 100 gives me 300, minus another 40 gives me 260, and minus another 4 gives me 256. All right, so I'm looking at, again, X squared equals 256. If I want to get just X, I'd have to take the square root of both sides. All right, let me get blue back in the party here. So I take the square root of both sides. Again, the power of 2 and the radical are going to cancel each other away. All right, you take the square root of a radical, you take the square root, take the square root of the power of 2, you get whatever was being raised to the power to begin with. All right. Then we just need the square root of 256. Fortunately, that's a perfect square, giving a value of 16. But definitely a little bit more work to do in this kind of problem. Right? So now we introduced the X. So if I just say X is equal to 16, you haven't answered the question. You'd have to say the longer side is equal to 16 feet. All right, so there's a lot more going on in this one, but still, it was a perfect square. I mean, it's nice. It doesn't always play out that way, but when it does, it's a good thing. We started introducing or reincorporating more terminology. Isosceles triangle ABC, and you got to think about what isosceles means. Base of 12 and legs of 10 each. Find the altitude to the base. Right, so talk to you about the structure of an isosceles triangle. Right, so with the normal orientation, make it look halfway decent. The base should be the obvious one. That's going to be the bottom. Right. The altitude extends from the vertex angle to the base, forming a right angle. Come on, lock in, close enough. All right, so that's an altitude. The other two sides of the triangle, those would be the legs. All right, so we have two legs of an isosceles triangle, but then by dropping that altitude, and that vertical line, in this case vertical, intersecting with the base and forming a right angle, we've created two right triangles out of this. Right, so they're giving us some information, but we have to place that information correctly. Right, so they said triangle ABC, so draw another isosceles. No, this time labeled up. The base is 12. I'll call it ABC. They said it's triangle ABC, so we can do that. It has a base of 12 and legs of 10 each. All right. So what we need to do is figure out the length of the altitude. So again, I could drop that vertical, forming a right angle. I need to determine this. All right. So what I'm going to do is I'm just going to pull out one right triangle. Going to yank that out here. See if I can do it. That didn't work. Well, that didn't work either. Let's see. Do it this way. All right. So by taking out this triangle, I know that this side is going to be X. The hypotenuse is going to be 10, is opposite the 90-degree angle. Now, one other fact that comes into play here is that that altitude is going to split the base into two congruent segments. So this segment is going to be the same as that segment. So if the whole distance is 12, then each part is going to be 6. All right. So now we get to this idea that, and I mentioned this before, that sometimes you've seen a problem before, and because of that, you know the answer, you don't have to do any work. All right. That's the muscle memory. That's what we want. You know, eventually, you know, if you're not already there, I'd like you to know that the square root of 8 is equivalent to 2 times the square root of 2, or 2 rad 2. All right. But, you know, until you practice, you don't really get there. All right. But if the same problem happens to appear on the exact same page as the question you're working on, then you can pull that information out, because we know in this triangle, the two legs of 6 and 8 correspond to a hypotenuse of 10. All right. So we have the hypotenuse of 10. We have a leg of 6. The other leg must be 8. So the X value is going to be equal to 8. And so that's going to be our altitude without showing any work or even doing any work. All right. That's useful information, but it's not always the kind of thing that you think to do. But what we come across are things called Pythagorean triples. They're numbers that come up fairly frequently using the Pythagorean theorem. Right. Now, because my memory's shot, I can't remember if I actually included, I'll come right back to this, Pythagorean triples into the notes. I did not, so I'm going to jot them down here. So right, they're in the form of leg, hypotenuse. All right, so leg, hypotenuse. I don't want to overuse a dash. So, I mean, colons. So leg, hypotenuse. Now, we just discovered that 6, 8, and 10 will work in the Pythagorean theorem. Meaning if I have 6 and 8 as legs, I'll get 10 as a hypotenuse. If I have a leg of 6 and a hypotenuse of 10, the other leg must be 8. So that's one relationship, 6, 8, 10, right? But if I take that 6, 8, 10 and divide each of those values by 2, I get 3, 4, 5, right? So if I divide each by 2, I get 3, 4, 5. That's another Pythagorean triple. Those would also work in the Pythagorean theorem. Meaning if I take 3 and square it, let me just do it this way instead of scrolling down 500 units. If I take 3, square it, add to it 4 squared, I'll get 25. That's what 5 squared is, right? So that checks out. 6 squared, oops, I don't know why that jumped. 8 squared, that gives a 100. That's what 10 squared is, all right? So any multiple of 3, 4, 5 would get the job done, right? So I could say 3n, 4n, 5n, where n is a whole number. Right? So, like if I wanted to do 30, 40, and 50, 30 squared plus 40 squared, 2,500 is 50 squared. Right? So that would be one set of Pythagorean triples. There's actually more. I'm going to reduce a little bit to get them in there. I'm only going to do the 3 popular sets. There's more. I mean, there are people that just kind of make it their personal mission to find all the different Pythagorean triples. That's people who get into things like number theory. But the ones that come up most frequently would be 8, 15, and 17. Right? And again, I would slap an n on those. Right? Because any multiple of those values would get the job done. So let's say I had 16, if I'm letting n be equal to 2. Right? If I have 16 squared plus 30 squared, that would be 15 times 2, is equal to 17 times 2 squared. All right, so that would be 34 squared, which would be the same number. So that's another Pythagorean triple. I didn't try the 8, 15, 17 because I knew that one would work. All these 3 numbers are just multiples of 8, 15, and 17. Right, they're in proportion. 5, 12, and 13 is the next set, or in the last set. So 5n, 12n, 13n. Right. So in each case, it's where n is a whole number. Right. So these are just general rules that help us identify Pythagorean triples. Now, it's not the kind of thing that you need to know. It's just a time saver. Right. Because that last problem, we were able to figure out the missing side just because we'd seen it before. But now anytime I see 6 and 8 as the legs of a triangle, I know that the hypotenuse is going to be 10. But if I see 12 and 16 as the lengths of the sides of a triangle, I'm going to know that the missing side is 20. Right? So Pythagorean triples really, really are useful in that regard. Right? So you can do it. You can even do it with sliders. I'll show you real quick. You just type in, I don't think I've used A and B in this. I tend to stay away from that. So a squared plus b squared. Right. Now, if you try to put in, I'll show you, try to put in the whole Pythagorean theorem, it's like, but what do you want to do here? It'll create some sliders and it'll just do nothing. Right. So that didn't help anyone do anything. But what I can do is I'll put in a squared plus b squared as one operation and create some sliders for that. So it'll compute a squared plus b squared for whatever I put in as a and b. And it could even be negative numbers if I want, right? The result should be equal to c squared, right? So whatever this number is, its square root is going to be the value of c, right? So if we look at it like, I'll just kind of do this off on the side here. If I want to figure out using a squared plus b squared is equal to c squared, what c is, right? Just the value of c. Remember, an option that I always have is to take the square root of both sides. Root being the second word of the day. Root, like as in square root, or the roots of a plant or a tree, right? So I'm going to take the square root of c squared, but I'm also going to take the square root of the other side, right? So these two, the power of 2 and the radical would cancel away, giving you c equal to the square root of a squared plus b squared. Right? So this is a rule. It's kind of an extension of the Pythagorean theorem. Right? So if I say, instead of a squared plus b squared, if I say the square root of that, oops, gotta get rid of that a. Then wherever I put my a and b sliders, it's going to tell me what the c value is. And you could put it in this case, you could put in c equals, and it'll still tell you the value. You won't get an error there. Right? They call this an explicit equation, where it's just like, what is, it's already solved for the variable. So if I put my a slider on 6, eventually, all right, use the Apple Pencil, and if that doesn't work, I'm going to type it in and put my B slider on 10. I'm sorry, 8. Okay, typing it in. You see the C value is going to be equal to 10. All right. If I put a 5 and a 12 for A and B, the missing side would be 13. That's this relationship. All right. But you could also have cases where you're going to have some radicals. Right. So let me do an example where that's the case. I have to add a page here to do that. I don't know why it's not in here, but I wanted to throw it in. So I'll throw in a blank page here. And it's just a quick side example. So for example, let's say you have a triangle, a right triangle specifically, where the hypotenuse, I'll give you the two legs. Let's say the two legs are 3 and 6, and we need to figure out what x is. All right. So it's still the Pythagorean theorem. A squared plus b squared is equal to c squared. The two legs are known. 3 squared plus 6 squared is equal to x squared. 3 squared is 9. 6 squared is 36. 9 plus 36 is equal to 45. You get 45 is equal to x squared. Now, when I go to take the square root, I'm doing this by hand, but I could also do it on Desmos. You're going to get a decimal, all right, which is telling us that we need to simplify rather than convert it into decimal form. Oh, this, okay, hold on. I don't know if it's going to crash. All right, so I'll put in the 3. I'll put in the 6. And you see I'm getting 6.708 and all that good stuff. All right, that's not pretty. All right. So the right-hand side is going to cancel down to an x, but that radical 45 I have to simplify. All right, so I break that down into the product of two factors, one of which is a perfect square. So I could use my table, right? Thinking about two numbers that would multiply to 45, one of which is the perfect square. right? So the two numbers that multiply to 45 would be 9 and 5. And so we would get 3 radical 5. All right. So that would be the length of the hypotenuse, 3 radical 5. All right. I'm going to do another couple of side examples here because this is going to build us towards the concept of triangle similarity. So let's say you have a square. Another example that should have been in the original handout. Not really very square-like, more rectangular. Let's say you have a square and you need to find the length of the diagonal. Right, and let's say the lengths of the sides of the square are, I'll just keep it simple. They're each 1. This is a 1 unit square. Right, 1 foot, 1 centimeter. Right. If I want to find the length of the diagonal, both diagonals in the square are congruent. And we'll get to proving why that's the case down the line. But for now, we're just going to take it on faith. This gives us 2 legs of the square, or two legs of the right triangle contained within the square as 1 and 1. All right. So I'd be looking at this. Not quite, but it's good enough, I guess. This triangle has legs of 1 and 1, right? Because it's this piece that's coming out to give us this triangle, right? We would need the hypotenuse, call it x. Again, a squared plus b squared is equal to c squared. If you try it on Desmos with the a value of 1 and the b value of 1, you get a decimal value. Now, sometimes you could recognize the decimal value. You know, through experience, I know that's radical 2, but you can't always count on that. There's a lot of decimals out there. Like to be able to expect to recognize them all is unreasonable. So we go through the process. 1 squared plus 1 squared is equal to x squared. 1 plus 1 is equal to 2. Fun fact of the day. 1 squared is 1. So each one of those 1 squareds is a 1, and 1 plus 1 is 2. So then when I go to take the square root of both sides, again, on the left, the power of 2 and the radical cancel, giving you just an x. On the right-hand side, I might have said left. On the left, it's just going to be a radical 2. So you get a radical value, but you're also able to draw a conclusion from this. And it's something that, it's not really obvious initially, but we're dealing with a square. So all angles in the square are congruent, right? Even these angles, right? So if these angles are congruent in length, if they're congruent in measure, then that makes this an isosceles right triangle, right? More specifically, if I know that this is 90 degrees and these two angles are the same, and there's 180 degrees in the triangle, 180 minus 90 is going to give me 90 left over, split between these two angles, this one and this one. So if it's split evenly between those two angles, 90 degrees divided by 2 is going to give me 45 degrees apiece. So this one's 45, and this one's 45. All right. So the relationship here is, and this is going along the lines of what we were talking about with the Pythagorean triples, is that if I'm dealing with a 45, 45, 90 right triangle, right? Well, 45, 45, 90 triangle, it's right because it's 90 degrees. So for a 45, 45, 90 triangle, 90 degrees, the sides will be 1n, 1n, radical 2n. So radical 2 times n, where n is a whole number. So this is basically a Pythagorean triple that's specific to this type of triangle. All right. So now again, it's a 1n. I know it looks like in, but you know. Best I can do. Right. So if I'm looking at, for example, sides of 2, 2 and 2, then I would expect the hypotenuse to be 2 radical 2. Right. So you can verify that. Plug in the 2, plug in the 2. That 2.828, blah, 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 that's double what we had on the screen previously. We had 1.414, 2.828 is double that, right? So if n is a whole number, you know, and by whole number, I mean anything bigger, well, 0 technically would be included, but anything bigger than 0 excluding decimals. So like 1, 2, 3, 4, like I said, you can include 0, but then you wouldn't have a figure. 5, 6, 7, 8, 9, all the way up to, you know, whatever reasonable large value you would have, it's going to work in the Pythagorean theorem. So if I had, let's say 15, well, actually I have a 10 and a 12 here. So I'll go 10. I can max out this one at 10 also. So I get 14.142. That's going to be equivalent to 10 radical 2. Right, same thing. But you get it without doing the work. Right. If you ever take a trig class, you know, and you know, for most folks, you're not going to take a class exclusively on trig, you know, like outside of a high school situation. But and even then, it's rarer and rarer now. Like, obviously, that's the one that's struggling. But if you take a trig class and find yourself working with trigonometry, this relationship becomes pretty useful. For now, for us, it's just really a convenient shortcut, although it doesn't seem very convenient right now. We're gonna do one more side example, and then that'll be it for class. Just a point of reference, because I was looking at the syllabus today because I was updating what I planned on teaching in this unit, and I swapped some things around. So I took out quadrilaterals and I replaced it with triangle similarity, and we'll do quadrilaterals in unit 3. But in doing so, I looked at when I said the date of the unit test for this unit would be, or the unit assessment, I should say. And in the syllabus, it said tonight, and I can't see any earthly reason why that would ever have been the case, especially a week after spring break. It's not even going to be next class because we still have a fair amount of material to get through. So the unit assessment will be in 2 weeks, right? So 2 weeks from tonight. I'll update. I'll put it out an update on Blackboard, but that is, let's see, April 6th. All right, so 2 weeks from tonight. Oh, Lord, it's almost here. So April 6th instead of March 23rd. Right, so April 6th for the second unit assessment. Right, just so you can kind of get your ducks in a row. Now, the last one. So another side example. I'm going to create an equilateral triangle. Now we know in an equilateral triangle that all the sides are congruent, but what you may not remember is that all the angles are congruent as well, right? All the sides are congruent, so each one of these sides are the same in measure, but so are the angles. All right. Now, if all the angles are congruent and there's 180 degrees in a triangle, that means each one has to be 60 degrees. So we have 60-degree angles here, here, and here. 60-degree angle. All right. Now, in the same vein as what we were talking about before, we can take a vertical line and drop it down to the base of this triangle. So I'll go from here to here. All right. That's going to create a 90-degree angle. Let's say just on the left side for now. I mean, it'll create it on the right side too, but I'm only going to focus on the left side. All right. So if I know that this is a 60-degree angle and this is 90, then that missing angle up here has to be 30. Got to be a 30-degree angle. One day I'll figure out a better way to do that. All right, so this triangle here, I'm reproducing over here, 60 degrees, 90 degrees, 30 degrees. All right. Now, let's say I tell you that the hypotenuse is equal to 1 of this triangle, which really just means that the original equilateral triangle had a measure of 1. All right, so I'm going to say that there's 1 unit around. All right, so that means my hypotenuse is equal to 1. All right, what we learned, I think it was on the last page, is that this altitude is going to split the base into 2 congruent segments. All right, so if all 3 sides are equal to 1, then each side or each segment of the base is going to be half of that. Right? Because they're equal in measure and they have to add to 1. So each one of these little pieces here is going to be equal to 1/2. Which means that this missing side here is 1/2. All right, so using the Pythagorean theorem, I could figure out the missing side over here. So I would write 1/2 squared plus x squared is equal to 1 squared. And again, that's the Pythagorean theorem. A squared plus b squared is equal to c squared. All right. When you square a fraction, you square the top and bottom independently. So 1/2 squared is the same as saying 1 squared over 2 squared, right, which is 1/4. So 1/4 plus x squared is equal to 1. Oh, that's not the squiggly line I was hoping for, squiggly curve. So 1/4 plus x squared is equal to 1. Right? So I can subtract the 1/4 from both sides. We would get x squared is equal to, well, 1 minus a quarter, $1 minus a quarter, 3/4, 75 cents. So I'd be looking at, when I take the square root, because I want to take the square root, I want to get that power of 2 out of there, the square root of a fraction. Right? So x is going to be equal to the square root. Well, we learned before And when you take the square root of a fraction, you take the square root of the top over the square root of the bottom. The square root of 3 over the square root of 4. The square root of 3 is a radical that can't be simplified, but the square root of 4 is equal to 2. Right? So that would be my missing side. Right? So radical 3 over 2. Now I don't have to worry about simplifying that any further because I only have a radical in one part of the fraction, and the radical I do have can't be simplified any further. Right? So then I can conclude here. So for a 30, 60, 90 triangle, so for a 30, 60, 90 degree triangle, opposite the 30-degree angle is going to be a 1/2. Opposite the 60-degree angle is going to be a radical 3 over 2. And opposite the 90-degree angle is going to be a 1. But I also want to allow for it to be multiples of that, those ratios. All right, so I slap on an n, 1/2 n, rad 3 over 2n, and 1n. And again, where n is a whole number. All right. So in the Pythagorean theorem, I mean, it's a little harder to compute, but I can verify if I plug in a 1/2, I'd have to type it in, but 1/2 for the A value, rad 3 over 2 for the B value, you'll see the C value is equal to 1. Right, so that checks out. That's what we just computed. But if I decided I wanted to make this, instead of 1/2, I would say 1/2 times, let's say 15. Then this would also be times 15. Let's say I'm making my n value 15. Then my C value should be 1 times that same 15. 1 times 15 is 15. All right, so it checks out. And what you get here between the Pythagorean triples and all of these little, I'll call them shortcuts, although, I mean, I don't think anybody's looking at the paper, and saying, well, this is definitely really short. It's not that I would be asking you to do all this stuff. It's more so that you would recognize that in a 45, 45, 90 right triangle, or a 30, 60, 90 right triangle, that these relationships would apply. So if you know one of the sides in a triangle, in a 45, 45, 90 right triangle, one of the sides is 1, the other side would necessarily have to be 1, then the missing side would be radical 2. All right. And there are extensions on this, and it'll work its way into our studies involving triangle similarity. But this is a good place to start. And you see how we're slowly building off of the review of radicals. They say that knowledge of square root radicals is something that students should come into this course being proficient with. In my experience, I've seen that people have come into this course being somewhat familiar with radicals, but in the past, I found that people have benefited from the lengthier review. So, I don't like to bore people with things that I know that they already know. But in the case of radicals, there's almost always some aspect of it that you're like, I wasn't sure about that. I'm glad we went over it. So hopefully that's the case. If not, then I just bored you to tears with something that you already knew, in which case that's not bad either, right? Because it's like, well, I already knew this, good. So then you're right where I need you to be, right? And nothing is lost from me. So I'm going to stop the recording. I'll leave the share up for a few minutes, but again, if you missed it, I keep saying test, the unit assessment will be 2 weeks from tonight, and instead of what it said in the syllabus tonight. It's not, obviously it didn't happen tonight, right?